Welcome, everyone. We're diving deep today into industrial wastewater treatment, and you've really outdone yourselves with the source material this time.
Oh, yeah.
Absolutely.
Yeah.
We've got brochures from companies like FRC Systems, technical articles, even some historical overviews. It's incredible to see just how much effort goes into cleaning up industrial byproducts.
That's a whole hidden world, isn't it?
Totally. And our mission today is to wade through all this information and extract those key insights. What are the need-to-knows about industrial wastewater treatment without getting bogged down in too many technical details?
Sounds like a plan. It's amazing to think how this field has evolved over time, from those early Roman sewers all the way to the advanced systems we have today.
Yeah, I was thinking about that too, reading about those ancient systems. It
Yeah.
really puts things in perspective.
Definitely. While the technologies have certainly come a long way, that fundamental goal remains the same, protecting human health and the environment by removing pollutants from water.
Absolutely. And speaking of pollutants, one thing that really stood out to me was the sheer diversity of industries that generate wastewater. I mean, just going through the FRC Systems brochures, you see everything from food processing to metal plating.
Oh, it's incredibly varied. Each industry has its own unique mix of contaminants, posing very specific challenges for treatment.
Right. Like those examples highlighted in the industrial wastewater treatment article. Food processing plants, for instance, they produce wastewater that's loaded with organic matter and nutrients.
Exactly. If that stuff were released untreated, well, imagine the impact on a river. Oxygen depletion, algal blooms, it wouldn't be pretty.
But definitely not the kind of place you'd want to go for a swim. And it's not just food processing. The article also mentioned textile dyeing. Those vibrant dyes often contain some pretty nasty chemicals.
Oh, absolutely. And we can't forget about oil refineries. Their wastewater can contain dissolved hydrocarbons, sulfur compounds, all sorts of things that you really don't want in the environment.
A real chemical cocktail. So how do we even begin to clean up such a diverse range of messes? Where does the treatment process even start?
Well, it all begins with what we call preliminary treatment.
Preliminary treatment.
It's the first line of defense, removing the big stuff, debris like rags, plastics, grit, things that could damage equipment further down the line.
Makes sense. So we're talking about screens, grit chambers, that sort of thing.
Exactly. Those are the workhorses of preliminary treatment.
Okay, so we filtered out the larger debris, but I'm guessing the water is still far from clean at this point, right?
You're absolutely right. That's where a crucial step called flow equalization comes in. Industrial wastewater can be, well, let's just say unpredictable. Sudden surges in volume, changes in composition, it can be all over the place.
And that's where flow equalization helps.
Precisely. It acts like a buffer, smoothing out those fluctuations and preventing shock loads to the more sensitive biological treatment processes that come next.
So it's about protecting those delicate biological processes, those microscopic cleanup crews we keep hearing about.
Exactly. Flow equalization ensures a more stable environment for them to do their work.
Speaking of those microbial heroes, can you tell me a bit more about how they actually clean up the wastewater? It always seems a bit like magic to me.
It is pretty amazing. We're essentially harnessing the power of bacteria.
Bacteria.
Yes, both aerobic and anaerobic bacteria. Aerobic bacteria need oxygen to survive, while anaerobic bacteria thrive in oxygen-free environments. Think of them as two specialized teams with different appetites for pollutants.
So it's about matching the right bacteria to the right task.
Precisely. For example, in activated sludge systems, we have these large tanks filled with aerobic bacteria. We constantly supply them with air, and they basically feast on the organic matter in the wastewater.
Activated sludge. So those tanks are like bustling microbial cities, teeming with tiny little cleanup crews.
That's a great way to put it, and they do a phenomenal job of breaking down those pollutants.
That's incredible. What about those anaerobic bacteria? Where do they come into play?
They excel at breaking down the tougher, more complex organic compounds that aerobic bacteria might struggle with. And they do it all without needing oxygen.
So that saves energy. Where do we put these anaerobic bacteria to work?
In anaerobic digesters. These are sealed tanks where those bacteria break down sludge, producing biogas in the process.
Wait a minute, biogas. So we're not just cleaning up the sludge, we're actually generating a renewable energy source in the process.
Exactly. It's a fantastic example of turning a waste product into a valuable resource. But speaking of sludge, we should probably address the elephant in the room.
The elephant in the room.
What happens to all that solid material we've separated from the water? It doesn't just disappear, right?
You're right, it's easy to forget about the sludge, but it's a crucial part of the whole process.
Absolutely. And that's where sludge management comes in. We need to handle it responsibly, minimizing its volume, stabilizing it to prevent environmental risks, and then figuring out the best way to dispose of it or, even better, reuse it.
And I'm sure there's a whole range of options for dealing with sludge.
Oh, definitely. We can talk more about those in detail later. But before we get too deep into sludge management, there's one thing that caught my eye in the FRC Systems brochures. They keep mentioning a technology called DAF. D-A-F-F.
DAF.
Yes. It seems to be a key part of their approach to industrial wastewater treatment.
That's a new one for me. I've never heard of DAF before. What exactly is it?
Well, DAF stands for dissolved air flotation.
Dissolved air flotation.
It's a clever technique for removing pollutants that don't readily settle out on their own. Basically, we dissolve air into the wastewater under pressure.
Under pressure?
Yes. And when we release that pressure in a special tank, millions of tiny air bubbles form.
Millions of tiny bubbles.
Exactly. And these bubbles attach themselves to pollutants, like oil droplets or suspended solids, making them buoyant and causing them to float to the surface.
So it's like giving those pollutants tiny little life rafts, helping them rise to the top where we can skim them off.
Exactly. It's a very efficient way to remove certain types of contaminants.
And FRC Systems seems to be quite fond of this DAF technology.
They are. They've actually developed some interesting innovations to optimize the process and make it even more effective. But we can delve into those details later.
Right, I'm intrigued. Let's take a closer look at DAF and see what makes it so special.
One of the things that really caught my eye was their use of non-proprietary pumps.
Non-proprietary pumps.
Yeah, for generating that mixture of water and air bubbles. It's called whitewater, and it's essential for the whole DAF process to work.
Whitewater. Okay, I'm following. And why are non-proprietary pumps so important?
Well, it makes their systems more accessible. You're not locked into using specialized, expensive parts, which is a big plus for a lot of industries.
That makes sense. Keeping things practical and reliable. What other clever tricks have they incorporated into their DAF systems?
They've also developed a really neat sludge dewatering grid. It sits right inside the DAF tank.
Inside the tank. Interesting.
As the sludge thickens, this grid helps to hold it in place, allowing it to self-dewater. Gravity basically takes over and pulls out even more water, creating a more concentrated sludge cake.
So it's a way to reduce sludge volume right from the start.
Exactly. And that can have a big impact on downstream processing.
Okay, so FRC Systems seems to have really thought through the practicalities of their technology. But what about those other aspects we discussed earlier, things like ease of operation and environmental impact?
Oh, they definitely highlight those points in their brochures. Their DAF systems are designed for automation. They have sensors that monitor the process and make adjustments to things like airflow and chemical dosing.
So it's like having a built-in expert managing the system, even if you're not a wastewater treatment guru yourself.
You got it. Less manual intervention means fewer chances for error and more consistent results.
That's a huge plus in an industrial setting where reliability is key.
What about the environmental side of things? Well, their DAF systems generally have a smaller footprint compared to some other treatment methods. They take up less space, and they tend to use less energy, which is always a good thing for the environment.
It sounds like FRC Systems has really hit the sweet spot, combining effectiveness, practicality, and a focus on sustainability. But I'm curious, where does DAF fit into the bigger picture of industrial wastewater treatment? It's not a standalone solution, right?
You're right. DAF is often just one piece of a larger puzzle. It's incredibly effective at removing certain types of pollutants, but it's not a magic bullet for everything.
Right. It's all about choosing the right tools for the job.
We often combine DAF with other treatment methods, like those biological processes we discussed earlier, to achieve comprehensive cleanup.
Ah, yes, those microbial heroes. We talked about how they come in two main varieties, aerobic and anaerobic bacteria. Can you remind me what makes each of them so special and where they fit into the treatment process?
Sure. Think of aerobic bacteria as the oxygen-loving workhorses of wastewater treatment. They're really good at breaking down the more readily biodegradable organic matter, and we often utilize them in activated sludge systems.
Activated sludge, those are those large tanks we talked about earlier, filled with bacteria and constantly supplied with air, right?
Right. It's all about creating the ideal environment for those bacteria to thrive and do their job.
And they do an amazing job. But what happens after those bacteria have done their work in the aeration tank?
Well, we need to separate them from the treated water. That's where the secondary clarifier comes in.
The secondary clarifier.
It's a settling tank where the bacteria, which are now heavier because they've consumed all that organic matter, settle to the bottom. The clarified water then flows out the top much cleaner than when it entered.
So it's like a giant microscopic filter.
You could say that. It's a really efficient way to separate those tiny bacteria from the treated water.
And what happens to those settled bacteria? Do we just dispose of them?
Not quite. We actually recycle a portion of that settled sludge, which is rich in active bacteria, back to the aeration tank.
Ah, so we're giving those cleanup crews reinforcements, making sure they're ready to tackle the next batch of wastewater.
Exactly. It's a very efficient and sustainable system.
Now, we also talked about trickling filters and MBBR systems as alternatives to activated sludge. Could you remind me what their advantages are?
Sure. Both trickling filters and MBBRs, which stands for moving bed biofilm reactors, rely on what's called attached growth. Instead of swimming freely in the water, the bacteria form a biofilm on a solid surface.
Attached growth, so they're basically setting up camp and waiting for the wastewater to come to them.
That's a great way to put it. In a trickling filter, the wastewater is distributed over a bed of rocks or plastic media.
Rocks or plastic media?
Yep. As the water trickles down, a biofilm of bacteria grows on those surfaces and consumes the organic matter. We make sure there's plenty of air circulating through the filter to provide the oxygen those aerobic bacteria need.
It's like a vertical garden for bacteria. But what about those MBBR systems? They sound a bit more dynamic.
They are. In an MBBR, we use small plastic carriers that provide a huge surface area for bacterial growth. These carriers move around within the tank, constantly mixing and ensuring good contact between the bacteria and the wastewater.
So it's like a microbial washing machine, keeping those bacteria in motion.
Exactly, and that helps to maximize their cleaning power.
So we've covered the aerobic side of things, but what about those anaerobic bacteria? The ones that thrive in oxygen-free environments.
Ah, yes. Anaerobic bacteria are the specialists for those tougher jobs. They're the ones that break down those complex organic compounds that aerobic bacteria might struggle with.
And they do it all without needing oxygen, which saves a lot of energy.
Precisely. And their domain is the anaerobic digester. It's a sealed tank where these bacteria feast on sludge or even concentrated industrial wastewater, breaking it down into simpler compounds.
And the best part is they produce biogas in the process.
You got it. It's a win-win situation. We clean up the waste and generate a renewable energy source at the same time.
It's amazing how much potential there is in something that we used to consider just waste.
Absolutely. And some facilities even produce more biogas than they need, becoming net energy producers.
That's incredible, turning a waste product into an energy source. But I have to admit, I'm a bit curious about the practical side of things. What do these anaerobic digesters actually look like?
Well, modern anaerobic digesters are designed to be completely enclosed, so they don't really have much of a visual impact.
And what about the smell?
They're actually much better than you might imagine. The enclosed design helps to minimize odors. It's certainly not a rose garden, but it's a far cry from the open-air pits of the past.
That's good to hear. So we talked earlier about how anaerobic treatment is particularly well suited for those high-strength wastewaters, the ones with very high concentrations of organic matter. What makes anaerobic digestion a better choice in those cases?
That's right. High-strength wastewaters can be tricky to treat with aerobic processes. You'd need a lot of energy to supply all that oxygen, and you'd end up generating a huge amount of sludge. Anaerobic digestion, on the other hand, thrives on those high concentrations of organic matter.
So it's like they're built for that kind of challenge.
Exactly. And as a bonus, they produce less sludge overall, which is always a good thing.
Less energy, less sludge, and we get biogas as a bonus. But I know there's more to wastewater treatment than just DAF and those biological processes. We briefly mentioned advanced treatment earlier. Can you give me a glimpse into that world?
Of course. Advanced treatment is all about fine-tuning and achieving those really strict water quality goals. It's where we go above and beyond the basic cleanup, and the methods we use depend on the specific contaminants we're dealing with.
So it's like the finishing touch is making sure the water is truly clean and safe.
Exactly. We might use filtration to remove those remaining suspended solids, giving the water that crystal clear appearance.
So we're talking about things like sand filters or multimedia filters.
Those are some common examples. And for those really tough to remove pollutants, like heavy metals, we often use chemical precipitation. We add specific chemicals that cause those dissolved metals to form insoluble particles, which then settle out and can be removed.
It sounds almost like alchemy, turning those invisible metals into something we can physically remove.
It's pretty neat. And then there are those even more elusive pollutants, things like pharmaceuticals, pesticides, personal care products, those emerging contaminants that are becoming a growing concern.
I've heard about those. They seem to be everywhere these days. How do we deal with those?
That's where we turn to some really cutting-edge technologies like advanced oxidation processes. These processes use powerful oxidizing agents like ozone or hydrogen peroxide, sometimes in combination with UV light, to break down those complex molecules into simpler, less harmful substances.
So it's like we're giving those pollutants a chemical makeover, making them more environmentally friendly?
Exactly. And then there's membrane filtration, one of the most impressive technologies out there. Membranes act like incredibly fine sieves, allowing us to selectively remove different types of pollutants based on their size and properties.
It's like having a whole arsenal of specialized filters.
You got it. We can use microfiltration and ultrafiltration membranes to remove bacteria, protozoa, and larger organic molecules. And for those really tiny pollutants, like dissolved salts or small organic molecules, we turn to reverse osmosis.
Reverse osmosis. I've heard that term before, but I'm not entirely sure how it works. Can you explain it?
Imagine pushing water through a membrane that's so fine it only allows water molecules to pass through. Everything else, like those dissolved salts and other impurities, gets blocked.
Wow. So reverse osmosis is essentially the ultimate purification step.
It's pretty close. It produces water that's incredibly clean and pure.
That's amazing. So reverse osmosis is used in a lot of different applications, right?
It is. From desalination, where we remove salt from seawater to create fresh water, to producing ultra-pure water for industrial processes and even for some drinking water treatment systems. And it's playing an increasingly important role in water reuse, allowing us to treat wastewater to a quality where it can be used for things like irrigation, or even, after further treatment and disinfection, as a potential source of drinking water.
That's remarkable. It really shows how far we've come in our ability to clean and reclaim water. But we've covered a lot of ground here, from those initial screens to these highly advanced treatment methods. And there's still one crucial aspect we need to discuss. What happens to all that sludge we've separated from the water?
You're absolutely right. Sludge management is a critical and often overlooked part of the wastewater treatment puzzle. And it's where those principles of sustainability and resource recovery really come into play.
All right, let's dive into the world of sludge and see how we can turn this byproduct into something valuable. Right, so we're ready to tackle this sludge, right? Turning it from a problem into a resource. But where do we even start?
Well, the first step is often thickening. We basically want to remove as much excess water as possible from the sludge, creating a more concentrated material.
Okay, so it's like squeezing a sponge to get rid of that extra water.
That's a great analogy. And we can achieve this using gravity thickeners, where the sludge settles naturally over time, or flotation thickeners, which use air bubbles to help lift the solids to the surface.
So we're either letting gravity do the work or giving those solids a little lift with some bubbles.
Exactly. Both methods are effective at concentrating the sludge and reducing its volume.
Okay, so we've squeezed out some of the water, but it's still sludge, right? What's the next step in this transformation?
Next comes dewatering. We're aiming to remove even more water to create a sludge cake that's easier to handle and transport. There are a couple of ways to do this. Centrifuges spin the sludge at high speed, forcing the water out, and then there are filter presses that literally squeeze the water out like a giant press.
So we're either spinning it or pressing it, all in the name of getting rid of that pesky water.
Precisely. And the end result is a much drier, more manageable sludge cake.
That makes sense. But even though it's drier, it's still sludge, right? What do we do with it at this point?
Well, that's where stabilization comes in. We want to make sure that the sludge is less likely to decompose and cause environmental problems. One common method is anaerobic digestion.
Ah, yes. Our old friends, the anaerobic bacteria. Those oxygen-hating heroes that break down complex organic matter and produce biogas.
That's right. We can put those bacteria to work in anaerobic digesters, where they'll feast on the sludge, reducing its volume, eliminating odors, and destroying any harmful pathogens. Plus, we get that valuable biogas as a bonus.
So it's a win-win situation. We're treating the sludge and generating renewable energy at the same time. Are there any other options for sludge stabilization, apart from anaerobic digestion?
There are. We can also use aerobic digestion, which is essentially an extended aeration process, giving those oxygen-loving bacteria more time to break down the organic matter in the sludge. And then there's composting, which creates a humus-like material that can be used as a soil amendment.
It seems like there's a whole range of options, each with its own benefits. But once we've stabilized the sludge, what happens then? What are our choices for handling this final product?
Well, one option is land application, where we carefully apply treated biosolids to agricultural land or forests. It's a great way to return those nutrients to the soil.
It's like completing the cycle, taking what was once a waste product and turning it into something that nourishes the earth. What other possibilities are there?
We can also incinerate the sludge, burning it at high temperatures to reduce it to ash. This drastically minimizes the volume, but it does require careful air pollution control measures. And then there's landfilling, which, while less common these days, is still an option in certain situations.
So the best approach depends on a variety of factors, like the type of sludge, local regulations, and available infrastructure. It's a complex decision-making process.
Absolutely. And thankfully, we're seeing a growing emphasis on those beneficial reuse options, like creating compost or extracting valuable resources from the sludge. For example, we can recover phosphorus from sludge, which is a critical nutrient for plant growth, but a finite resource. This helps reduce our reliance on mined phosphorus, making the whole system more sustainable.
It's incredible to see how sludge management is becoming an integral part of the circular economy, turning what was once a waste product into a valuable resource. But what about those industrial wastewaters that contain heavy metals or other toxic substances? Can we still reuse that sludge?
That's a great question. Sludge containing heavy metals or other hazardous substances definitely requires special handling. It might need to be treated as hazardous waste or disposed of in secure landfills. But there's a lot of research happening right now focused on finding ways to safely extract those metals and other valuable materials from the sludge. It's about turning a potential liability into a source of valuable resources.
It's inspiring to see how we're continually pushing the boundaries, finding new ways to tackle these challenges and create a more sustainable future. It really highlights the ingenuity and dedication of the people working in this field.
I completely agree, and it's that drive for innovation that's shaping the future of wastewater treatment as a whole.
Before we wrap up, I'd love to hear your thoughts on what the future holds for this field. What trends are you most excited about?
Well, sustainability is undoubtedly at the forefront, pushing us towards reducing water use, energy consumption, and greenhouse gas emissions. We're seeing a movement towards decentralized systems, treating wastewater closer to its source, which opens up exciting possibilities for on-site reuse. And then there's the incredible impact of digital technologies. Smart sensors, artificial intelligence, these are transforming how we monitor and manage treatment plants, making them more efficient and responsive.
It sounds like we're entering a whole new era of wastewater treatment, one where innovation and technology are not only helping us to clean up our water, but also to create valuable resources and build a more sustainable future. It's a really exciting time to be following this field.
I couldn't agree more. There's so much potential for positive change, and I can't wait to see what the future holds.
Well, we've covered an incredible amount of ground in this deep dive into industrial wastewater treatment. We've explored the intricate processes, the innovative technologies, and the crucial role of those microscopic bacteria. But most importantly, we've seen how this field is evolving to meet the challenges of our time, driven by a commitment to protect our precious water resources and create a more sustainable future. It's been a truly fascinating journey.
Absolutely. It's been a pleasure sharing this journey with you and our listeners. Hopefully, we've shed some light on this often invisible world and sparked some curiosity about the incredible work being done to keep our water clean and safe.
So the next time you turn on the tap or flush the toilet, take a moment to think about the amazing journey that water has taken and all the effort that goes into making that possible. And remember, even something as seemingly mundane as wastewater could be a source of innovation, resourcefulness, and hope for a brighter, more sustainable future. Thanks for joining us on this deep dive.